Hello friends, I am Samir and I welcome you all to your own YouTube channel Aryabhatta. Friends, today our topic of discussion is inverse of a square matrix. So, what is the definition of the inverse of a square matrix? For that, let us take two square matrices of same order. I will tell you why actually we are taking square matrices just later on. So, for now let us take A and B, which are two square matrices of the same order and the order is n, and they satisfy a certain condition here. That means, product of A B is equals to the product of B A, B with A, and that is equals to the identity matrix of the same order n. That means, A B is equals to B A is equals to I n. So, we are taking A and B which are same order square matrices such that their product is commutative and it results to the identity matrix of the same order n. So, here if they satisfy certain conditions, then we can say that B is the multiplicative inverse or simply the inverse of the matrix A. So, B is the inverse of the matrix A, which is denoted by the symbol A inverse here like this, and here similarly A is called the inverse of the matrix B, which is also symbolized as B inverse as this symbol. So, here A and B, they both are inverses of each other. So, if the product of two matrices are commutative and equals to the identity matrix, then those two matrices are said to be the inverse of each other. So, here if a matrix whose inverse exists, then it is called a invertible matrix. That means, not every matrix has inverse. That means, it is not guaranteed that if you are taking a matrix, then its inverse should also exist always. So, what is the condition so that we can ensure that the matrix we are discussing is invertible? That means, its inverse actually do exist. That we will discuss later on. Now, come to the first point, that is it not possible that we will take rectangular matrices and we will find out the inverse of rectangular matrices. Is it not possible? So, here I am going to tell you that what is the problem with a rectangular matrix and its inverse. So, the definition of the square, the definition of the inverse of a square of a matrix, the definition of the inverse of a matrix is that it should be its product with another matrix of same order should be commutative. That means, if you are taking A and B as two square matrices, then only of the same order, then only their product will be commutative. That means, A B is equals to B A. But if you are taking two rectangular matrices A and B, then there are many chances and there are all possibilities that their product will not be commutative. That means, in case of rectangular matrices, A B is not equals to B A. So, they will not satisfy the necessary condition required for the inverse of a matrix. So, friends, that is why it is very much essential to take square matrix only to find the inverse. Now, what are the conditions that is required to find that a matrix is invertible? The required condition is that we can see in this property that a square matrix A is invertible if and only if it is non-singular. That means, its determinant value should not be 0. If a matrix is singular, that means its determinant value is equals to 0, then it is not invertible. Okay, friends. So, now we come to know two or three things here. The first thing is, what is the definition of the inverse of a matrix? The inverse of a matrix is another matrix which, when multiplied with this matrix in from any side, from left side or right side, it results to the identity matrix of the same order. And if the inverse exists, we say that it is invertible. If the inverse does not exist, we say it is not invertible. And when it is invertible, It is invertible if it is non-singular, that means its determinant value is not 0. If the determinant value is equal to 0, then it becomes singular and non-invertible. Now, secondly, we come to know that why a square matrix only have inverse, why not a rectangular matrix? Because of this commutative property that it need to satisfy as the product. So, only square matrices of same order satisfy the commutative property of products. That is why only square matrices do possess inverse, not rectangular matrices. Now, let us see one example, friends. Here I am taking two matrices of same order, 2 by 2 order both, and if I am multiplying them, the result is I am getting as the identity matrix of the same order. That means, here the left side two matrices are both invertible, that means they have inverses of their own, and these two matrices are both inverse of each other. That means, the first matrix inverse is the second matrix and the second matrix inverse is the first matrix. Okay, friends. Now, come to discuss few properties of the inverse of a square matrix. First one, I already told you that the square matrix A is invertible if and only if it is non-singular. Second property says that if I am finding out 2 times inverse, that means inverse of the inverse of a matrix is result to the same matrix. Third property says that if you are finding out the inverse of the transpose of a square matrix, then that is same as the transpose of the inverse of the matrix. That means, you can interchange transpose and inverse with each other. Fourth property says that if the determinant value of the inverse of a square matrix is equals to the reciprocal of the determinant of that matrix. And the fifth property is based on the definition of the inverse of a matrix. That means, if you are multiplying the matrix with its own inverse in any side from left side or from right side, then the result is the same order identity matrix. Sixth property says that if you are taking a matrix A and you are multiplying A with itself up to k times, and then of that matrix you are finding the inverse, then that will be equals to the product of k times product of the A inverse with itself, where k is definitely a natural number. Now, seventh property says that the inverse of an identity matrix is itself same, and the eighth property says that the 0 order matrix is not invertible. A 0 matrix is never invertible. A 0 matrix do not possess any inverse matrix. Ninth property says that if a non-singular matrix is symmetric, then its inverse matrix is also symmetric. Then our next property is, if A is a matrix which is a diagonal matrix where the product of the diagonal matrix is not equals to 0, then its inverse is equals to another diagonal matrix of the same order where the diagonal elements are the reciprocal of the individual elements. That means, you change A by 1 by A, B with 1 by B and C with 1 by C, and you will get the inverse of the original matrix. And the same law also holds for right diagonal matrices. Here it is the left diagonal matrix and here it is right diagonal matrix. You can see only right diagonal elements are existing, others are 0. Its inverse also hold by the same formula. You can see, you can verify by taking some examples yourself also. Now, the 11th property says that the inverse of a matrix, if it exists, is unique. So, before we discuss that, the inverse of a matrix may exist, may not exist, but if it will exist, then it will be unique, that means one and only one. So, a matrix will possess only one inverse matrix. So, more than one inverse of a single matrix is not possible. So, we can prove it also here, which is very simple. Let us take a square matrix A which has two inverses, say B and C. So, B and C both are inverses of the matrix A that we have taken. So, if B and C both are inverses of A, so they will definitely satisfy the definition of the inverse of a matrix, and the definition says that the product of a matrix with its inverse is commutative and results to the identity matrix. That means, as A is the inverse of B or B is the inverse of A, that means A into B is equals to B into A is equals to I, and similarly as C we have taken as also the inverse of A. So, A into C is equals to C into A is equals to I. Now, let us start with the matrix C, because we have to show that C and B both are not different matrices, they are same matrices. So, let us start with C and let us make them equal with B by simplification and calculations. So, C I can write as C into I, because if we multiply the identity matrix with any matrix, the result will unchange, I know. So, C is equals to C into I. Now, in place of I can write A into B. Now, I am getting the result C in the bracket A into B. Now, we know that the product of three matrices is associative. So, I can change the bracket. So, I will take the bracket out of A B and I will put outside C A. So, it is C A inside the bracket into B. Now, C A, the product of C A is equals to I. So, I will put the value I here. Now, I into B is again B. So, in that way I am proving that C and B both are equal, they are not different, they are same. That means, there is only one inverse of A, not both different. So, the inverse of a matrix is unique, is proved in this way. Now, the 12th property says, is a very important property, that if A and B both are invertible matrices of same order, then the inverse of the product of two matrices A B is equals to the reverse product of their inverses. That means, inverse of A into B is equals to B inverse into A inverse. We can prove this also, friends, as we have to prove that the inverse of A B is equals to B inverse into A inverse. So, let us use the nature of definition of the inverse of the matrix. The definition of the inverse of a matrix says that if two different matrices are inverse of each other, then their product should be the identity matrix. So, let us take A B and this total matrix B inverse into A inverse, and let us multiply them together, and if we can prove that the product is I, that means they both will be inverse of each other. So, let us multiply them. We can use associative law as usual, and we can take the B from the first product to inside the second product. So, it will become like this. Again, using associative law, I can make a group of B with B inverse, and B inverse both are inverse of each other. So, their product will be by definition identity matrix. So, it will become I. Now, I inverse when multiplied with A inverse, I when multiplied with A inverse will become A inverse by the nature of product of identity matrix. Now, when A is multiplied with A inverse, by the definition, same definition of inverse of a matrix, it will become identity matrix. So, in this way I prove that A into B whole of B inverse into A inverse is equals to I, and I can also prove them taking in the opposite order. That means, I can prove that B inverse into A inverse whole multiplied with A B is also equals to I. So, in this way, if the product of two matrices is equals to I, that means the inverse of one is the another one, that is proved. So, here you have to be very sensitive. We cannot write A inverse into B inverse, because we know that multiplication of matrices is not commutative in general. So, A into B whole inverse is B inverse into A inverse, that we proved. Now, we can find out, we can make it a general statement also. Here we have taken in the property 12th, we have taken only two matrices. Say I am taking the product of n matrices, and of that I am finding the inverse. So, the inverse of the product of A1 with A2 up to An will be equals to the product of the inverses of individual matrices taken in the reverse order. That means, An inverse into An minus 1 inverse up to A1 inverse. So, friends, this is all in definitions and properties of the inverse of a matrix. Hope you understand this topic. Thanks for watching this video, and please do subscribe this channel. Thank you very much.